I'm going to say hi.
Why would you say that?
Because here in my notes it says ho can be proven and has equal sign.
I love it. So you can't have any more of a situation where you don't have an equal sign than when you have a freaking not equal sign, right? So that is a good thing to say. I like the way you said it with almost conviction. So this is definitely got to be the high. Because what's the opposite of not equal to? Incredibly enough, it's equal to. I love it. So that's got to be the ho. So the ho is always going to be the one that has some kind of equals in it. Either expressly has an equal sign. I think the book always has equals, so I kind of disagree with that. Either it has an equal sign or has a less than or equal to, greater than equal, some kind of equal to statement in it. That's the one I cannot prove. I cannot take a sample and prove that a mean is something. Because the sample will almost always be not the real mean. But I can show that a sample is so far away from what somebody thinks that I think that that can't be right. That's the whole point of hypothesis tests. We can always try to prove this, to show support for this, to try to reject this at the same time, but we can never try to prove this. I never accept the H naught. I just have not disproven it yet. Yes, am I with me a little bit? Okay. So this is definitely going to be a two-tailed test. And the instructions on this homework, by the way, if you look at what they say, test the given claim, identify the null hypothesis, alternate hypothesis, blah, 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 blah. Basically, all the steps I show you fit into what they ask you. So if you just use the steps that I've shown you, you'll be answering the things that they're asking you. Is that cool? We do them a little bit out of order from what they want it, and we don't care. We can deal with that. So the first step is always, what the hell are we talking about? This is what we're talking about. Second step is, what am I allowed to use to talk about this, and why? Can I use Z, T, or nothing here? What is it that we have to look for there? Two things. Yeah, is it normal?
Greater than 30.
Good. So we know the sample size here is only 16, right? Oh yeah, so I love that last question. Look at the very last question he asks. And this is where on this step you would actually say nothing, but I'll go ahead and do it anyway. This is page 418. Technically, it's nothing. Why is that? Because of what you just said. Do we have what you just said? They don't tell me anywhere that this is normal. And what's the sample size?
16.
It's not big enough. So n equals 16, less than 30. But if we assume it's okay to go ahead. Then what's the next step I would look at? So right here, this technically says I can't do anything. So if you actually left this homework problem blank, I can't fault you. Because technically it says you can't do anything. But assuming we can, just forge ahead. So like we did on the test, where it said assume you can and just do it. What do I look at next to tell me the difference between these two things?
Standard deviation.
Yeah, standard deviation. What kind of standard deviation do I have? And then again, this is a weird problem. It's a good one to ask because their statements are weird, but what really helps me is I know them in this section where sigma is known. But the way they say it is really weird. Assume that the standard deviation of, they should say all outcomes. That would have made it a lot more straightforward, right? Because I'm always looking for words like all. Population standard deviation would definitely give it away. So here, sigma is known. Z-scores. If we're going to use anything, we can use Z-scores. Technically, we can't do anything. That's the answer to that last question. What is it about the sample that tells me something might be wrong? Well, it's not big enough. But we're going to go ahead and try to do the steps anyway. How you guys doing so far, Zach? So there, if they would have said from the sample of 16 rolls, we get a standard deviation of blah. That would have been S. Then we would have used t-scores. Cool. I love it. So what's step 3? Now that we know we're going to do z-scores, we're going to set up the rejection region. What's good enough evidence? What's sufficient evidence to reject the null? So what is it that I have to look for here? We know it's a two-tailed test. That's number 1. What else do I need to know to figure out where the rejection region is? What do I need to be told? Besides what the rejection region is, that would be great.
Confidence interval?
Not confidence interval, but it's related to that. It's a little fish dude, right?
Alpha?
Alpha. The level of significance. So what's the alpha in this case? Do they say? Yes, they do. They don't use the symbol, but they use the words. I love how some of you guys are like, Jeff, it says it, but somebody say it for me, make me happy.
0.05.
Yes, you make me happy. Okay. So alpha is 0.05. Cool. So it's a two-tailed test. Alpha is 0.05. Why would it be different if it was a one-tail? I'm going to get a z-score when I look this up. Where am I going to look this z-score up? Strangely enough.
0.025.
I could use 0.025 if I really want to, but the t-score chart is set up for 2 or 1 tail. So I could just look at 0.05, 2 tail, on the t-score chart. Let's see if I brought one with me. Yay. So if we look at 2 tails, 0.05.
1.96.
Yeah, look all the way down to the bottom, we get 1.96. I love it. So how am I going to really draw this thing? Where's 1.96? Or is that question kind of misleading? How many tail tests? 2. So what do I really have? Negative 1.96 and 1.96. Cool. This should feel very familiar. It's almost like making a confidence interval, because what do confidence intervals do? How many tails do they naturally make? 2. So a 2-tail hypothesis test should feel like a confidence interval. You should see similar numbers to what you're used to, because they are basically the same thing as confidence intervals. So how in the world do I say this in words? If z star, where am I going to reject the null? If it gets inside one of those 2 regions, right? So if z star is, what about negative 1.96? Less than negative 1.96. Or z star is greater than 1.96. Reject the Ho support. So again, I mean, this class is an almost continuous reminder that it's so easy to get wrapped up, or actually so easy to get like, what the hell's going on, Jeff? There's so much shit going on. You forget the basic idea. I want to set up a benchmark. I want to say, you've got to show me evidence. Not only can your sample not be equal to this, it's got to be so not equal to this that it's evidence that this is wrong. Because I know if I just took a sample, if you just roll die, if you don't get a 3.5 mean, are you freaked out? Of course not. If I got a 3.5 mean perfectly, that would freak me out. It's more likely to have something slightly different from that. If I take a sample, it's not going to be the real mean. So it's not good enough to be a little bit different. You got to be freaking different. You got to be out here. You got to be down there. Your sample's got to be far away from this to be evidence, because it's just a sample. Sample's going to be different. It's got to be so different. It's like, whoa, shit. Maybe. Right? I mean, that's the idea here. These steps. What are you talking about? What are you allowed to use to talk about it? What's going to be good enough evidence? Did we find good enough evidence? I mean, that's the basic steps. But what's really important here is, what's the benchmark? Did I make it? Step 3, step 4. Those are the important steps. What's the benchmark? Did I make it? Right? So now we're at step 4. Did we make it? What's the sample information that we have? What's X bar? 2.9375. And what's sigma? We know sigma from the beginning. We know it was 1.7078. We know it's a sigma dude. N is 16. So what do I have to do before I make a z-score?
So
Change the standard deviation, 11. That's for individuals. Now I need it for groups of 16. So it's the old dude divided by square root of 16. 0.4269. 0.427, is that right?
0.42695.
So 427, we'll say that's pretty good. And now that I did that, what can I do to compare it against this dude? I can find the z-score, the z-star in this case, right? So the general formula for a z-star is this. It's only slightly different from the normal z-score formula we've been using. The normal was x minus the mean divided by sigma. Well, now I don't have x's, I have x bars. I have a sample that I've taken. So I do my sample, it's always my stuff minus the mean, and we assume this is the mean. We say, assuming you're right, let's see what happens. Divided by the new standard deviation. So it's always my data minus the accepted middle divided by the right standard deviation. In this case, the new standard deviation. So let's see what we get here. X bar was 2.9375. The mean we're saying is 3.5. Standard deviation for this one is 0.427.
Negative 1.32.
Could be. Yep, negative 1.32. That's Z star. Alright, so did we make it far enough away? This says, alright, you gotta be here or there to show evidence that this is wrong, that this is right. I can say he's wrong, I can say it looks like he's right. We only got to negative 1.32. So here's 0. We got about here. That is different from the mean. We know it's different from the mean, but is it different enough to show evidence? No. That could have just happened by random chance. It's not unusual enough to get that, to say that this looks to be wrong. So before we go to the last step, which is everybody's favorite step, which is where you have to write your conclusion, I could get the p-values here. The p-value is not going to be what you think it is, and hopefully you all have a thought about how to get this. How do I get this p-value? What do I do? What is the p-value in general? Alpha is the area in these tails. The p-value is the area in my z-scores tail. The only thing is, since this is a two-tail test, what did we do to get alpha set up here and there? We had to cut him in half, right? So if I just looked here, wouldn't have to double it to get that back? You guys with me? How much area is in there? 2.5%, careful. 2.5%, so I have to double it to see that again, right? So whenever you have a two-tailed test, you look up your area and you double it. Just to make it fair. How can you compare to alpha if it's not the same idea? So how much area is in here? If you look that up, negative 1.32. How much area do you get? Yeah, 0.0934. So the p-value would be twice that. 0.1868. That's the p-value, 0.1868.
Is that the two-tail test or one?
That's only for a two-tail test. This is a two-tail test. we have to double it to make it fair. I want to compare the p-value to alpha. This is bigger than alpha, so that's another reason why I failed to reject. We didn't make it here.
Double it? If you're just looking at that one side.
I love it. So, to be honest, and I don't agree with all the methods we use, but to be honest, I think we should cut this dude in half. But isn't it equivalent? Either I cut him in half, or I double him. Either way, it makes it more fair. So the alpha gets cut in half to go there and there. Right? You guys got it with me? So the p-value, whatever I get, should either be doubled to make it fair to compare to this guy, or this guy should be cut in half to compare to my actual area to make that fair. Let me try this again. All right. Let's take a little side step. Somebody help me out. How much area is in here? This is the normal curve, all this kind of stuff. Somebody look that up for me. Yeah, it should be 0.05. Right? This should be 5%. Alright, so, now stay with me. So which means, if this is a two-tailed test, what was alpha then? What would alpha have been? Alpha would have had to have been 10%. Point went up. You guys with me? Okay. So remember, if the p-value is less than alpha, if the p-value is less than alpha, you reject the null. And all that means, and when I first taught statistics, I really did not like teaching that part. But then it became obvious that you need this for business, you need this for other things that you go into after you take statistics. You have to understand what p-value is. It's very, very simple. Very simple to understand that if I get here, I rejected the null. You guys with me? If I get a sample that's right there, that's far enough away, I can reject the null hypothesis. I can say, it looks like this guy's wrong because I am way the hell out there. So I compare z-scores to do that. But the p-value actually is really important. It tells me the level that I can use to actually pass this test. So let me make this a little more concrete. Let's say I get a z-star of negative 1.5. Did I reject the null? Did I make it far enough away? No, because I'm right here, right? Cool. I didn't make it far enough away. So what's this guy's p-value? What do you?
0.0668.
0.0668. Okay, cool.
Times 2.
And then you gotta multiply that by 2 to get the p-value, right?
0.1336.
And the reason is because, again, if I only compare this one side, it's not fair. Let me see if I can create one that's gonna do what I want it to do. Let me see. Oh, well, that's exactly it. I forgot I'm doing this kind of backwards from what I'm used to. You have to multiply 2. If I stop right there, I set it up the way I want to. What was the alpha again? 0.10. Isn't that less than that? So by this rule then, wouldn't that mean I reject the null? But what, did I reject the null? Did I make it far enough away? Why does it seem like I made it far enough away? Because what happens to this? I cut it in half. Right? The first thing I do to this is cut it in half to put it there and there. So it's not fair to compare this to this. Now I agree with you. I personally would rather cut this in half than compare those. We could have set the whole thing up to be like that. You and I weren't around when they first set this up. so they didn't have the benefit of our counsel. Too bad for them, right? So we've just got to deal with, and it's equivalent mathematically. If I could cut this in half, it's equivalent to double this guy. They end up telling you the same thing. If I don't double him, it looks like I did it. Did we do it? No, we didn't make it far enough away. Shit. I got to double it to make it fair. So I double this and I get the 0.1336, whatever it is. And now that's bigger than that. So I failed to, I didn't get less than the alpha. I failed to reach it. And real quick, why does this make sense? Because if I have let's look at a one-tail test for a second. If this is alpha here, and I'm in here, if my z-score is in there, isn't the tail of my z-score going to be smaller? So they say the same stupid thing. This is why I didn't really understand when I first started teaching stats. They say the same thing. If my z-score is bigger than the benchmark, then in this case smaller because it's negative, then I reject the null. Well, if my tail is smaller than that one, I still reject the null. That's really all this says. If my tail is smaller than the alpha, that means I'm further out. That means I'm further out. They say the same thing. Okay.
But now it's bigger
Say again?
than in this.
Oh, but remember, here, in this example, did we get far enough away? No. So this is bigger, so that means, did I reject the null? Looking at the p-value? No. Looking at the z-score? No. Thank God they agree. They have to agree. I can't get both situations. You failed and you passed. Congratulasucky. I don't know what that means. To make up a new word. Right? Do they blend? Apparently they do. Okay. Let's do a few more. We have two things going in here. Chapter 8 is the most in-your-face example of this. We have the nuts and bolts that we all desperately want to get. And then we have the idea behind the nuts and bolts, which every now and again surfaces. You know, you can do all the nuts and bolts, and then you get to these conceptual questions, you're like, let me pass those. Right? But you got to get those too. So let's do another problem. That's really the best way to do this, is just to see several of these kind of problems and see how they work. Anybody else have a specific one you want to look at, or? I kind of want to do one from section 8.5 now. Actually, I want to do... Yeah. Number 20 on page 429. Oh, on the last one we never did write the conclusion, but we'll write it here. So look at number 20. See how far you can get. Let's try to set this up. Claim, hypotheses. I'll tell you what. Well, we'll talk about that. Try to get as far as you can. You don't know what to do for A, but you know what to do for B and C. Awesome. Start there. Do what you can. Bless you. Now they refer to data set 13. If you're flipping back there, don't worry about it. They actually already did the analysis. But if you look at problem like number 25, 26, you'll have to come up with your own X bar and S. And we know how to do that. You put them in list 1. You do 1 bar stats. We're out of chapter 3. I'm not going to make you do the standard deviation by tables. Screw that. Let the calculator that you paid so much money for, somebody that you know did. Right? Let that do the work. This problem, they did the work for us. Sweet. Don't look at data set 13. No need for it. So let me catch up to you guys a little bit. What's the claim in Mathish? They actually spell it to you in the exact English translation for math.
It's equal to...
Exactly. Mu is equal to 120. You gotta love it when they just say it directly, right? Which one is that going to be, the ho or the high? Yeah, the ho's got to have an equal sign that has an exact equal sign. So it's got to be the null, if you prefer that. And then what's the H1 guy, the alternate? Not equal to. I like it. So how many tail tests will this be? Two tail tests, because to be not equal to, I can show it's greater or less. I don't care. What do you guys get for part B? Which one? Oh, yes, ma'am.
So for the HI, I know you're putting not equal. Isn't there going to be times when there's going to be reasons to put equal instead of not equal?
For the H1?
Yeah.
Never.
Really? It's always going to be...
Always. It's always going to be, have no equal sign in it. Always.
Okay.
Right? Which one is our claim?
HL?
Yeah, this is the claim here.
Uh-huh.
On the last one we did, the claim was actually H1. Because the claim was not equal to. It was not equal to that. Right? That was the last one we did up on the board. So there's nothing at all that determines which one it's going to be besides the fact that the H1 cannot have an equal sign in it. And the HL must have an equal sign in it. And why is that? Because the H1 is the one I can prove. I can never prove an equal statement using a sample. If I give the whole population, then hell yeah, I can prove the equal statement because I can see everything. We can't always do that in statistics. So I can never prove an equals using a sample. But I certainly can show evidence that I can disprove that. It looks to not be that because it's so far away in either direction. Right? So this one must be the one that I can prove. Provable. Cool. All right. And this one's rejectable. I can reject an equal statement. Jeff, you are 38. No, I'm not. Look at my birth certificate. I reject your equal statement. Screw you. Right? But I can't prove it. Z, T, or nothing. What do we look at? Two things.
Normal.
It's normal. Why is it normal? N equals 40 greater than 30. Central limit theorem says good.
Sigma is known, so...
Careful. Where does our standard deviation come from?
Oh.
It's sample. So we sigma unknown. So what do we use? T-scores. Cool. So the whole reason T-scores were invented were to cover our ass from we don't know sigma. We don't know the population standard deviation. We only know the estimate, the sample standard deviation. What do I need to know for the rejection region? No, it's two-tailed. I know it's a T-score. What's alpha? Yeah, 0.05. So you want two-tail t-score. So for t-scores, what else do I need to know? Degrees of freedom. What's the degrees of freedom going to be? I'll wait till you write it, Jeff. There you go. All right, it's 39. All right, just one less than the sample size. Cool. So what do you get when you look that up? You look up two-tail, 0.05, and you stop at 39. If you stop, you get a t-score. If you don't stop, you get a z-score. So 0.05, two tails, 39. What do you guys see? Neat. 2.023? Yep. So T is 2.023. So what will it actually look like here? Considering it's a two-tail. So it'll be down here, it'll be negative 2.023 and positive 2.023. Cool. So to put this in words, if my T star in this case, if my score for my sample is less than this or greater than that, we reject the null. Support the alternate. If we get far enough away, we can say it looks like it's not equal to, it looks like it's actually not equal to. So we reject the guy that says it's equal, and we support the guy that says it's not equal to if we get out there. It's just so far away. Now, I don't make a big deal out of, I know you guys are in this class, so you don't have the best feel for this. But the formula for z-score never changes. And technically it's a freaking t-star. Who cares? It's a z-score. I'm going to calculate my score for my sample. It's always the same formula. In the book, they make a big deal out of z is x bar minus the mean divided by standard deviation. T is x bar minus the mean divided by this standard deviation. Does it really, truly matter? No, I just always divide by the appropriate standard deviation. Who needs more and more formulas when the idea just makes sense? Like, it's always the same formula. So what do I know from my sample? I know x bar is, where'd it go? 123.59. S is 0.31. N is 40. And this is where people freak out a little bit. I said, you still have to do this. You still have to. This does not, when you do this kind of thing, when you do this step, sigma over square root of n, you do not make it into a sample. No, you don't. You can't make it into a sample standard deviation. You make it into a standard deviation for groups. What's this? Standard deviation for individuals. Came from a sample, I know, but it's for individuals. I need the one that's good for groups of size 40. I still have to do this step. I still have to modify it. When you do that in general, you're not making it into a sample standard deviation. No, you're not. You can't do that. Either there is or isn't that. I'm making it into one that works for groups of size, whatever. And here, let me make this a little more broad now that we're going to get these smaller things. When I say 3 decimal places, what I truly mean is 3 non-zero numbers. So 0.005.
0.004901.
I like it.
02.
0.049, something. That's beautiful. So you can stop right there. Because obviously, if the standard deviation came out to be 0.00000000098 and you rounded to 3, you say, well, standard deviation is 0, Jeff. Well, that's shit. You know it's not 0. So when I say 3 places, I actually mean 3 non-zero places. I normally don't have to worry about that. I normally don't get such small numbers. Yeah?
So how did we get that number? Because I got
Oh,
0.049.
that's all right. Let me see. Divided by square root of 40. 0.049. Oh, just 1 0.
Okay.
If you'll notice, I actually did not do it. But you guys certainly correct me the minute something's wrong up here. I'm kind of crowdsourcing the work here as I'm doing the explaining. So to get the z-score, it's always the same. I take my data point, minus the mean I see here, divided by the standard deviation. Right? So my z star will be my data, 123.59, minus this number, 120, divided by the new standard deviation, 1049. And that's just going to come out to crazy big.
I got 73.265.
Yeah, it's insane. Yeah. So what does that mean? Where do we go? What's going on here? Where are we? We're basically, here. Right? You guys with me? We are 73 standard deviations away from the mean. Is that evidence that this is wrong? If it was this and I took a sample, shouldn't I be close to it? Within, in this case, it used to be within 2 exactly, right? That was the beginning of weird, unusual, was 2 up and down. Now it's a little more precise. Here's 2.023. But does it really matter in this case? We're at freaking 73. Forget about it. So did we reject or fail to reject? Oh, we rejected the hell out of it, right? Reject the null, support the high. So the step that actually ends up making people the most annoyed, believe it or not, is the very last step. All this right here, you will get. If you've gotten the rest of what we've done this semester, then this is just a matter of getting used to the steps. The math in here is not very difficult. The ideas are actually old ideas, right? Just kind of repackaged. What ends up giving people the most trouble is the conclusion. But you use the words we just wrote. What's our claim? Which one was our claim? The whole nine, the no. So then I use these words. The conclusion is always going to reference the claim. So you make sure you use the one of these that references the claim. Our claim in this case was the null. So we have... Did we succeed or fail? We succeeded in insane amounts, right? We have definitely found sufficient evidence to use these words, reject, in place of this, put that the actual claim is, reject the claim that the mean voltage is 120. Now the one thing I skipped, because I wanted to finish this out before I talk about this, was the p-value. And if you think about it, how do we find p-values for z-scores? We look them up in the z-chart. And why is the z-chart actually so cool? Because it's very detailed. My z-score was 2.98. Just look up 2.98, right? The t-chart, it's much simpler to look at, but not very detailed, if you guys realize what's going on here. It's not very detailed at all. So I'm going to attempt to tell you how to do this. And I'm going to have faith that many of you will be able to do this. But it is a little weird. So we had a two-tail test, right? Two-tail. And we got degrees of freedom of 39. And we got a t-star of, it's like t-star, but who cares? Oh, this is insane. I don't even know why I'm putting this up here. Basically, the p-value for this would be, what do you think? How much area is outside of 73 standard deviations away from the mean? How much area is beyond that? Essentially 0. There's 100% below it, basically. So the p-value here would be basically 0. It's about 0. Why is that? Because the p-value is in the tail that my score makes. That's way the hell out there. How much area is still out beyond this far? Nothing. Basically nothing. Maybe something in the 80th decimal place. But for normal humans, that's 0. If this wasn't so insane, you guys with me? I'm going to make up a number right now, just to show you how this works. Because this really came out insane. If this would have been more like, 2.91, let's just say. You guys with me? Because I happen to have a problem here. It came out with an ugly number. I'm just going to replace it for a second to explain something. This is definitely not the same as the z-score chart. I can't look up individual t-scores here, can I? Not really. I get ranges of t-scores. So my degrees of freedom was 39. And my t-score that I got was 2.91. And 2.91, do you see how it's less than this? I mean, on this side of this. Do you see how they kind of go down from here? So where's 2.91? It would be over here. If I got exactly 2.7, my p-value would have been 0.01. Because that's where I go to get the area and the tails. And again, what's the p-value? The area and the tail or tails. Right? So my t-score would have been 2.7. I would say my p-value was 0.01. My t-score, if it's 2.9, then my p-value is less than 0.01. That's the best I can say. I cannot be very precise with the t-score chart because the t-score chart is not precise. Sounds like circular logic, but it is. That's how it is. It's how it's set up. It's not very precise, so you can't be precise. If you don't quite get that, I'm not going to make a huge deal beyond what I just did for p-values for t-tests. You guys hear what I just said? If you do not quite understand this for t-scores, I'm not going to be anywhere near as demanding on that. You better know how to do p-values for z-score tests, because that should be relatively easy. That's like section 6.2, like all over here. Okay. Let's look at this one, I think. Let's finish out this. This is the one that we started the last time. And then we'll do some new stuff. And actually, let me interject something a little more interesting. I know some of you guys are like, almost anything. Which one is from Jeff, so. That Hitachi screen. So I didn't say anything about it. There you go. Any of you guys ever heard of Google Trends?
Mm-hmm.
And it's an awesome place to go and do correlation analysis, actually. And back in 2000, what was it, 8 or 9? What they did was they did, it's really, really cool. It's called big data. So the more data you can get your hands on, the less you've got to be so precise up here. Why do we have so much trouble in some of these areas? Because we're only working with a sample. If we only had all the freaking data, or like a large amount of data, like it says at the bottom of the T-chart, everything would be so much easier. Well, we got computers nowadays that are insane with their space, right? So we should be able to do large data. So what Google did was they researched the terms people used over the last however many records they had. And they plotted when people would search certain terms versus when flu amounts went up. People would start going to the doctor and so forth. And they found the certain key terms that people search that would indicate that a rise in the flu is about to happen. And you look through, you can read the abstract. We developed an influenza forecast model based on real-time, geographically focused, and easy-to-access data, blah, 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 blah. Right? Forecast models designed to predict 1 week in advance for when the flu was going to start to break out. And obviously that's good information to have. Hey, the flu's going to break out in a week. All the docs can then go, oh shit, let's set things up for that. Now this gets really into don't worry about a forecast model with negative binomial, blah, 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 blah. What I really want you to focus on is where is it, Jeff? Oh, here. Overall, the p-value of adding this external information to the model is 0.0005. Is that evidence that the external information of search words in Google, is that evidence that it actually influences the outcome of this model? Yes. That p-value is crazy small, isn't it? I don't even have to tell you what alpha is. It's smaller than any alpha we use normally. That's why in the real world, and here's something I want to let you know. Alpha is kind of a big deal in here, right? In the real world, there is no alpha. In the real world, you just report p-values and let people make up their own mind. You have your own personal alpha. No, for evidence for me, it's got to be freaking plain 0.00007. Well, then screw you. I can't prove anything to you. Right? But everybody needs their own alpha. Compare that p-value. Let me back up and make sure you can understand. When they added the information about search terms to their forecast model, this is what this says. The p-value of adding this external information to the model is this. So when they did that, the increase of efficiency, how much better it did, it was this likely that it would have done that just by chance. You with me? Like if you get more sleep the night before, you get a higher grade on your test, you can say it's because of sleep, but maybe not. Maybe you would have just made a higher grade on your test anyway. But here they're saying the chances of that being true, that it would have just happened, even if they wouldn't have added this information, is that. So what's more likely? It actually made it better. That's an example of a real-world hypothesis test in action. Saving people's freaking lives, right? If I didn't have a way to make people wake up, when researchers see a p-value like that, they go, whoa, let me look at this. Because it tells them that's crazy evidence that something's going on here, right? Now obviously if you search, it doesn't give you the flu. And that's the whole silliness of when we first started talking about correlation. Does that really matter? No. What's more important is if I see people searching these terms, that tells me that they're probably starting to get these symptoms. And the more I see that, the more likelihood there is that there's going to be a flu outbreak very soon. So let me make some room in my hospitals. Let me get some information out to people. Here's what you do if you got the flu. You guys kind of with me? Okay. You can do this for almost anything. Any journal. Very often, somewhere they're going to have p-value references. If it's some kind of analysis they're doing. It's crazy. Okay. This is to me one of the coolest things, though. It's something that happened in all of our lifetimes. You were not young enough that you weren't aware of this somehow. I'm sure most of you guys have heard something about this maybe. If you don't know Google Trends, you should look. It's really cool. Are you stretching? Okay. Alright, so let's go back to this. Just calm down, Jeff. Just get back to that. So remember this here? We started this one last time. We had the pain reliever that we were trying to prove worked better than the old one. So our claim was our pain reliever gave relief in less than the old one, the 11.2 minutes. So we went through the steps. It's definitely a one-tail test because we say in less time. We showed that we have to use t-scores because we don't know the real standard deviation. Our standard deviation came from the 45 test students, right? Don't worry, I'm not going to suddenly start feeding you stuff and see what happens. The degrees of freedom, we had to go down, remember, to 40. You always are more conservative with that. So this is where we left off. We got a t-score of 2.021. It's negative, of course, because it's down there. We have to put the negative sign on there. So we left off on these last two steps. So let's finish this up real quick. And I'll do this again. We'll see if we have a more reasonable p-value to talk about again real quick for the t-score. What do I know for my sample? What was the x bar for my sample? We did a better 10. Yeah, 10.4. And what was S? Yeah, 2.34. And N was 45. So the first thing I have to do is change that standard deviation. Let me do this with you so there's no dissension out there. Let's see. So what do you guys get for the new? Yeah, 0.3488, so like 0.349. Cool. And now we can make our Z star or T star, I don't care what you call it. It's going to be the same formula basically. It's always going to be my data. Oh, Jeff, you need a point there. Minus the mean from the claim up here, the mean from the hypothesis statements, 11.2. This is a stray mark. Divided by the new standard deviation. Do it again.
Negative 2.92.
Negative 2.92. That's so freaky.
Negative 2.292.
2.292?
Yeah.
That's even better. Okay, good. 2.29? That's a little better. Thought I had some ESP going on, but no. Not really, Jeff, too bad. So right there, I can answer the question right now. Did we get far enough away or not? How far away did I have to get? Negative 2.021. I got negative 2.29. Did I get far enough away?
Yeah.
Yes, I got in there. There I am. So I made it into the rejection region. And why do we call it the rejection region? Because if you make it in there, you can reject the...
Claim?
Which, not the claim, the no. Right? The no. You guys are uneasy with me saying hope. I know. So we can reject the no, support the alternate. Why can we do that? Because we made it far enough away. We said this is enough evidence. Well, we blew past that. We showed enough evidence. Now, if you're interested to get the p-value, the degrees of freedom we used was 40. We got a t-score of 2.29. So if I look at 40, 2.29 is right in between these two. So my p-value would be, and this is a one-tailed test, right? My p-value would be in between 0.01 and 0.025. My p-value would be in between 0.01 and 0.025. What do you got? There it is. If you don't quite understand why that's true, don't freak out about it. I'm not going to make a big deal of it. I'm hoping some of you guys can see that. Definitely should understand why we did this. Now, which one of these happened to be our claim on this problem? The high. So I'm going to use this language now. Do you guys, I desperately want you to see how the conclusion should be the easiest part. Right? You're done with all the work. The conclusion should be the easiest part. You look at what the claim was. The claim was the high. I want to say then, I want to use this language. We have found sufficient evidence to use this language. Support the claim. Don't say support the H1. Not good enough. Support the claim that... What the hell is going on in this problem? Oh yeah. Our new drug brings relief in less time than the old one. You just go up and you use the exact same language for the problem. You go up to the problem, you see what the claim was, and you use the exact same language, right? The conclusion should be the easy step. Zoom out a little bit. So let's go to a couple from one of the sections we skipped over, the section 8.3. We'll do actually maybe one problem from there, and we'll call it a day for right now. nice thing about section 8.3 is that all the steps are the same. But before we get into it, remind me, remember these guys? Blah, 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 and then we had this one here. What effectively is this piece here? What is that effectively, comparing it to the first one? No, this whole thing is the error. I am talking about this piece here, compared to what's up here. And of course, that's trying to be a sigma, not an alpha. What is this? Standard deviation. So what's this got to be? Standard deviation. You know, as I say it like me. You guys say my way? So any z-score formula. So in section 8.3, we're going to say, I think that fewer than 60% of gross bond students smoke, or whatever. So now everything's going to be about percentages now. So I'm going to have n's and p's and q's running all over the place. I've got to use the formulas that work with NPQ for standard deviation. I still want to get a z-score. I still want to see what my z-score is. But I can't use sigma over square root of n. There's no freaking sigma in baseball. No, there's no freaking sigma in NPQ. For PQ problems, right? I have to use this guy. So when we get to step 4, when we get to the step where we're doing our z star, I'm going to divide by this, because that's the standard deviation in this case. Just like I divide by this when I'm talking about means. Same exact idea. So section 8.3 actually is very little new in there. It's kind of nice. Every single section in this chapter is basically the same format. So let's do one page, what, Jeff? I don't know. Page 409, number... let's do. Number 12. Is there a more interesting one? Nah, that's good. So number 12 says, company drug test success provides a test for marijuana usage among 300 tested subjects. Results from 27 were wrong. Use a 5% significance level to test the claim that less than 10% of the test results are wrong. Okay, so you approach this the same way you do the other hypothesis tests we talked about. The very first thing I look for, I don't care about anything else, the very first thing I look for is the claim. That's where I start. And then I start doing my normal steps. So what claim is being made here? What's less than 10%? What do I put here? Is it a mean? Do I put mu? No, it's a percentage. I put p. So just like the other hypothesis tests had mu's running around in here, and then in step 4 we had x bar running around here. I'm going to have p's running around here, and in step 4 I'm going to have p hat running around, right? Exactly the same way. There's so many analogies here. It's crazy. It's exactly the same steps. So which one is that, of course? And why is it not HO? No equal sign. So this would be H1, alternate. What's the no going to be? In the book, they just have an equal to sign. And the reason I don't like that is because my claim could be, I think it's at least 10%. Then I've got to be able to write greater than equal to. That's what at least 10% means. I've got to have a greater than equal to sign. So I kind of disagree with them. They always have an equal sign here. If you always want to put an equal sign there, I can't fault you. The book does that. And that's the book I'm using, so what can I do? But really, these should be exact opposites of each other. This is the claim here. One or two tail test? One tail. Beautiful. Because it's just less than, I'm interested in just less than. Now you're going to love this about NPQ problems. It's an NPQ problem, right? I know that because they're talking about percentages. NPQ problem is Z or nothing. It can never be T. Because the whole idea is, what do I check to see if it's normal? What do I check to see if it's normal? Who's got, no. That's for means stuff. I'm talking about percentages.
NP, NQ greater than 5.
Beautiful. All right, NP and NQ greater than 5. So what's N? How many people did they test? 300. So N is 300. So what's, and P is 0.10. So then I say, okay, what's NP then? 10% of 300 is 30. That's greater than 5. NQ has got to be the rest of the people. 270. That's greater than 5. Check. So the beautiful thing about NPQ problems is it's either normal and I use Z-scores, or it's not normal and I don't do a damn thing. There's no T-scores here. That's awesome. Let that be nice. And you can see that. You can actually see that. Here's these formulas again. How many p-hat formulas are there? Yeah, there's 2. How many p-hat formulas are there? 1. And what's the only thing it has in it? Z. How many X-bar formulas? 2. And it has a Z and a T, right? That tells you. Hypothesis tests are going to have the same thing going on. 2 options for hypothesis tests for means. 1 beautiful little option for p-hat. For percentages. It's either normal and you use Z-scores, or it's not and you do nothing. If this is normal enough, we use Z-scores. Let that be nice. If it's a percentage problem, you go, thank God I don't have to use T-scores, I don't do degrees of freedom, all that kind of business. Awesome. What about step 3 here? Rejection region. What do I have to, and this is beautiful, this is exactly the same as before. I still have to know it's a one-tailed test. I can use Z-scores. What's alpha? What is alpha for this? 0.05 again. They like 0.05. So help me out, look that up. One tail, 0.05. What Z-score is that?
1.615.
Yeah, good. 1.645. And that's going to be down here, right? So it's got to be
Negative.
11. You guys cool? You guys see that? So again, that step sets up how far my sample has to get. Now let's see how far my sample actually gets. So step 4. If I'm trying to prove something about P, what is it that I get from my sample? So compare to that. What's the sample equivalent of P? Just put a little, careful, that's the sample equivalent of mu, p-hat. And how do you get p-hat? You just look at your sample and you do the right percentage, right? What do I see in my sample? Out of 300 people, so out of 300, what happened? Out of 300 people, 27 had incorrect results, right? Yeah, 0.09. Awesome. So, and here's the beautiful thing. I only need P, I don't really need Q-hat. Q-hat's 0.91, that's great to know. But the formula, what do we always assume? We always assume that this is correct. We always assume, okay, saying that P is 0.10. So then I use P. I don't use P-hat and Q-hat. So here's the formula in general. My data minus the accepted middle, right? This guy. So it's always my data minus the accepted middle, so it's accepted to be 10% in the middle. I'm trying to prove that it's less than that. Divided by the standard deviation, which is, like I said earlier, but I don't have any hats on them. Why do I not have hats on them? Because I have P. P is 0.10. I don't have to use p-hat. So do you guys get the feel this is exactly the same steps as before? The z-score formula is a little bit different. You know, the z-star. So z-star here would be 0.09 minus 0.10 divided by the square root of 0.10. Q would be, if P is 0.10, Q is 0.90, yeah. Divided by N, which is 300. So be real careful. If you want to put this all in at once, you better put it in like that. So do this with you. Sweet. All right, good. That's what I was hoping. So what do you guys get there? Yes, ma'am.
It's supposed to be P or P hat in the square root.
The only time I have to use P hat, and remember, in the confidence interval, why do I have to use P hat and Q hat there? The whole purpose of a confidence interval is this because I don't know what P is. I'm trying to get a feel for what P is. Here, I know P. I'm assuming that's right. Let's say it's 10%. So I know P is 10%. I know Q is 90%. I'm going to use those then. I'm only going to use P hat and Q hat when I have to, when I don't know what P and Q are. But the whole thing about hypothesis test is, okay, let's say you're right. Let's say it's 10%. So we're going to use 10% in there for P and Q. There's no hats on that one. And again, I can't, if you do that a few times, I can't blame you that much because confidence intervals pound it in your brain that there's hats on those things in there. So it's hard to kind of let go of that quick. But what do you guys get for that z-score there? Yeah, so like negative 0.58. So what could we say there? Did we make it far enough away? We only made it about like there. Just a little over half a step below the mean. That could happen. That's not a big deal. It's not evidence of anything. So what can we say right there? Did we reject the null? Did we get it? Did we reject the null? No. So we failed to reject the null. So if we can't say he's wrong, if we cannot say he's wrong, we cannot say he's right. If we can't say this guy's wrong, we can't say this guy's right. So we fail to support the high. We failed all around. We failed big time. We did not make it out far enough. So we failed in every respect. It's bad for us. So how do I write this conclusion? Which one was the claim? HO or H1?
H1.
H1 was the claim, so we used this language. So we have we failed. So we have not found sufficient evidence. To support the claim that, what was the claim? That less than 10% of the marijuana use tests were wrong. So that's bad news for this test. I mean, if you can't show that less than 10% are wrong, that's bad. I can't really trust it too well. Because then 1 out of every 10 people at least would be getting wrong results. That's not good. Alright, so here's what's happening next time. On Wednesday, on a quiz, on chapter 7 basically. On the confidence interval stuff. Alright, so it could be something from 7.2, 7.3, 7.4. So we'll start with that, and then we'll just get right back into confidence intervals. Just more examples of those. Oh, yeah.
Happy Monday.
Yeah, so when we finished up the package.
This week ended up Thursday, right?
Yeah. Yeah, last week.
That was good. Also, in the summer, I was doing that house. And, you know, I had the 2 other teaching talks, which one's like better?
Yeah, 2?
Yeah.
Wow, I don't even know who's teaching anything, honestly.
It's,
Do you remember the names?
It's a money thing that works.
That's not helpful.
Very vague.
I don't know, dude, I gotta look it up. I can't remember who's teaching calculus. I think we have 2.
It's so 180.
Oh, if Arturo's beyond teaching it too, his class.
Arturo?
Yeah, I've taken so many of his algebra in his class. He gives you cheat sheets. The only problem.
It's the only determinant. Yes. Oh, no, that's not the...
If I can learn before semester for summer school, is there can you like how can you see me so you can get a warm up for going? My last class was free talk and it's been over a semester since I did work. So like if you know the for the summer, could I get some like sheets just like kind of get warmed up?
Yeah, I can give you what I got.
Okay. Yeah. Sorry, I should have.
Sure.
Okay.
What is the bottom equation?
Oh, this guy?
Yeah.
That's the one from 7.2. That's the percentage.
What's under the